I know we're all sleepy, but let's take a minute. Let's take a minute to do that. In fact, let's all stand up for a minute. Because otherwise we'll pass out. Just standing up. If you can, close your eyes and not teeter over, do that. If you are worried about teetering over, then keep your eyes open, please. Please, please, please. And while you're standing up, tucking your belly, so like kind of tightening your belly just a little bit. It pulls up that front, letting your shoulders fall down and back, just very gently. And then rising up like there's a balloon attached to the top of your head. So a very gentle upward pull. Notice what it feels like to stand. More importantly, notice what you notice. Where does your mind go? If your mind is going places that aren't involved in standing, the sensations, the experience, come back to this simple standing. And bring your attention to your feet, where your feet meet the earth rising up to meet your feet. What is that sensation? What is the shape of that sensation? You have a mental image of your feet, but if you didn't know what shape they were, what would they feel like? And let's start class. That's good. Good suggestion, person who suggested this. Reminded me of this suggestion. Let's see, so. What's going on?
We've got some NFL trades.
Oh, okay. Yeah, I don't know anything about that. You don't want my input on anything trade-wise or financial. Ask Alexander.
I learned firsthand.
There's still hope.
It's coming back.
It's coming back.
It's coming back.
I kind of forgot about the pre-class quizzes for a little while. You may have noticed. No one mentioned it for some reason. So there is one for Wednesday, but it's actually, I'm going to start doing them a little differently. I'm going to start having them be what we've already covered.
Yes.
So doesn't that make just more sense?
Yes.
Yeah, it does. So this has been a learning experience for me doing this class, as I constantly blame Cybert for whatever. Are we actually running? Would you mind checking for me, please? I feel like we are. You are. Awesome, thank you. So yeah, we're gonna, the second half of the semester, I'm owning it all. And so there's gonna be some chain rule stuff on the quiz. Also, midterm grades are due on Thursday by noon. So this class was based on certain criteria. There was like, you had to have a certain number of skills checks. And we're about halfway, we're almost to the halfway point. So what I'm gonna do is just take all the criteria that we have and have them to base your midterm grade. Does that make sense? So if an A was like 20, I don't even remember, I'm just 24 to 28, it's not that loose. You would need like 12 to 14. We haven't even had 14, so that's not going to be the scaling, but I'm just going to cut everything in half. And if you end up like getting a midterm grade that you're like, what the hell, just let me know and we'll talk about it, or you can just keep in mind midterm grades are just midterm grades. I don't know. Does anybody have someone like monitoring their midterm grades and was like, what is this? I'm paying good money for this.
That would suck.
That would suck. I hope that's not true for anyone here. So, onward. I got two things I want to talk about today. The first one's pretty chill, and it is differentials. And then the next thing we're going to talk about is the multivariate chain rule, which is kind of cool. There's going to be some diagrams. Chain rule is always a painful thing for lots of people in general. It actually might be a little easier with multivariate, is what I'm thinking. This might actually be something that if you had trouble with it, might make it a little nicer. So first off, let's just take where we started. I got a function of two variables. This all can extend to more variables, any number of variables you want. Remember how we made the tangent plane for this thing? Let's take a look at the tangent plane equation. So recall, here's my freaking pens. There we go. That purple pen that was on the, I don't know where that came from, but that's definitely my pen. My pen, that's right. So how did that work? So the tangent plane at point x naught, y naught, and then z naught. And the relationship was that z naught is the output for x naught, y naught. So this should all look kind of familiar. Slowly we're making our way back into calculus 3. Everything okay? You all right? Okay. So remember the equation of the tangent plane. It was z equals the z naught, so this was the f at x naught, y naught, plus the partial derivative at our point of interest times x minus x naught, plus the partial derivative in the y direction at x naught, y naught, and then we had y minus y naught. Take a second while you slowly acclimate yourself back to that. That shouldn't look crazy. We'll find out. I'm going to hand back your tangent plane problem set. I forget. It was so long ago that I graded them that I don't remember who that might be crazy for. But we've all been here. And I'm just going to make a little tweak here. I'm going to subtract the z naught from each side. And then I'm just going to like put fx times x minus x naught plus fy times y minus y naught. Keeping in mind that this is a scalar, this is a constant that I got from this. This is that, this is that. I'm just trying to be, I guess, lazy and just try to get my way through this with less writing. So notice here that, and let's draw the picture too, actually. So I've got this weird surface like this. I've got the point x naught, y naught, z naught, and at that point I've created a tangent plane. And I'll get out of your way in a second. So I've got a tangent plane, which is a flat thing, and it's touching right at that point there. Let me actually make it look like this stuff's behind there just a little bit. So that's underneath there. There we go. So this tangent plane is an approximation of the surface at that point. X naught, y naught, z naught. And you can see here that at that point, it's precise. This tangent plane literally goes through the point x naught, y naught, z naught. If x is x naught, this is 0. If y is y naught, this is 0. And I literally get z has to be z naught. So the tangent plane touches the point that I'm interested in. But as I move away from that tangent, from that point of tangency, it starts to not be as good an approximation. Thinking about just a simple sideway view of a tangent line and a curve that it's tangent to. You're perfect at the point of tangency, but as you move away, things get less good in terms of approximation. So this is pretty good right there, but if I came out here, that's a terrible approximation. Same thing is happening here. So one thing I'd like to just do is rewrite this. Let's say that I moved out to a point x, y, z on that tangent plane. So I'm moving out to that point. Actually, leave off the z. So I'm at the point x, y, and then there's two z values. Okay, hold on, sorry. So down here in the x, y, z plane, there's a point x naught, y naught. Oh, that actually looks pretty good. That's not too bad, I think. So this is the xy coordinates that I stuck in to get that surface, and I've got this tangent plane sitting above this curvy thing right here. So this point right here is this point right here. This is on the plane. Let me just change what I'm writing here. And this point is on the surface. We can use the plane to approximate what's happening on the surface as long as we don't move too far away from this point right here. You can see that this is a terrible approximation for that true value. So let's put here, this is the true value. And then on the plane is the approximate value. So one thing we might be interested in knowing is, if I move away from this point right here, a little bit in the x direction, a little bit in the y direction, how much does the z output change? And we can come over here and just easily make this with a new notation. So this is going to be delta z. Think of change in z. This is change in x, and this is change in y. And so if I rewrite this thing, it's dz equals fx. I'm going to actually put the coordinates back in. dx plus f with respect to y, dy. And this right here is called the differential of the original relationship. And let's notate what some things are. I've kind of loosely said it, and I'm being a little spastic too, so I apologize for that. So dx equals the change in the x direction away from x naught, y naught. dy equals the change in the y direction away from x naught, y naught. And dz is how much the plane, the z coordinate on the plane, has either gone up or gone down, or maybe even stayed the same. Bless you. So, thank you. So this dz is the change in height on the tangent plane. And it's approximately how much the actual function changed. So let's write that up here. So dz equals the approximate change. I'm going to write it a slightly different way. Approximate change given dx and dy, changes in the x, changes in the y direction. But it's only approximate. And this is only good for small magnitude dx and dy. So I don't want to move too far away. Otherwise, the surface is peeled away and then it's a pretty lousy approximation. We'll take a look at some very specific examples of how to use this. The true change is what is the z-coordinate here versus what is the z-coordinate after I move over to here. So if I move to this point xy, so in other words, let's say I move over to the point xy down here, and I look at my new output value, I can measure the exact change. This is f here minus f here. So let's write delta z equals the true change given dx, and here we can write that as equals delta x, and dy equals delta y. Just so you know, dx and dy will always be the same as delta x and delta y. It's just the change in the input. That's something we know for a fact. But when we talk about approximating the output, we use dz. When we talk about true change, then that's going to be delta z. So that's equal to your new, that's equal to your x plus dx. So x naught plus dx, y naught plus dy. So perturb your inputs by these amounts. And then subtract off where you were originally. And that's your true change. And then what we want to put here is that delta z is approximately dz when, let's actually introduce a little bit of cool notation. When these things are small. Have you seen this notation with the double inequalities before? Is that like a science thing?
Yeah, we use
Okay.
it.
And it means tiny, right? Kind of greatly less than 1. Is that what it means in science? Okay, cool. So this just means that the absolute value of these things is tiny, very small. And that's it. So let's actually do an example. This would be useful in cases where maybe you have some code that you're writing and you want to iterate over and over again and do some computation quickly, as opposed to having to invoke sines and cosines and exponentials. Where's my filthy rag? Anybody see it anywhere? No, I didn't take it home this time. Thanks, Camilla. Looks like nothing didn't get cleaned in any way. So good. Nice and got all that good math karma built up inside of it. Let's do a quick example. Ooh, I think I might even have some kind of real example. Nah. I don't even have a real example written down. Let's see, do I? I feel like I did. No, that's for chain rule. Because I know I've got science spoken here, and I'm trying to make you happy. Because I'm always trying to make people happy so they're not mad at me. Because my mom was always angry. So I spend my life trying to make sure no one's angry at me. Am I talking out loud or am I just thinking those things?
We didn't hear anything.
You didn't hear anything, okay. Cool. Therapy. All right, so example. Let's say z equals, let's do something very, very chill, x squared minus y squared. And let's say that we want to approximate the change in z as xy moves from 1, 2 to 0.92.1. So read the problem, make sure you understand what I'm saying. me change colors. So what I'm going to do is actually crank out the differential. This is f of xy right here. So recall that dz is equal to the partial of that with respect to x at the point of interest. I'm just going to put this up again, times the change in x, plus the partial with respect to y at the point of interest, times the change in y. And we'll have a cool way to write that in just a few minutes. Bless you. Sneezer person. So, hey, could you actually crank up what's, just do these on your own real quick. What's that? Just to make sure we're still, you know, sentient, calculus-wise. Find those two partials for me real quick. I need to give you something that'll take longer before I can hand back stuff. So hopefully soon. And hopefully that wasn't too taxing. Right? They're not even mixed. We don't have x's and y's mixed, so all the partials are chill. Is there any questions on those? Just refreshers? Okay. Cool. So, dz, the formula is going to be, now I'm going to plug in x naught, y naught. That's this. So that's x naught, that's y naught. That's the place I'm trying to understand change around. So this is going to be 2 times 1. That's this derivative evaluated at this point 1, 2, times dx. I'm going to go slowly. Let's not fill in the dx yet. And then the f with respect to y was negative 2y, so it's going to be negative 2 times 2. So again, this is fx at 1, 2. This is fy at 1, 2. And then times dy. And once I've got that, I've got a really beautiful formula. Super chill to work with. It tells me that my approximate change, dz, is going to equal twice the change in the x direction minus 4 times the change in the y direction. So it's really elegant, right? It's a nice linear relationship here between this change and this, even though we started with something not linear at all. So for the change here, what is dx? As I change from here to here, what's dx? Is it positive 0.1? Negative 0.1, right? So dx is negative 0.1. So use dx equals negative 0.1, and then what was dy? Same thing, but positive, right? 0.1. Does everybody see that? Make sure you get how I got the dx and the dy. So we should be able to approximate the change. We're going to actually find the true change, but dz is equal to twice the dx minus 4 times the dy, and that's negative 0.6. So we expected the z value went down roughly negative 3/5. Doesn't tell us what we expect the new z value to be. Let's go and find the true change now. Let's find delta z. And remember, that is the true change. So to do that, I'm going to take f, the function, at 0.9, 2.1, minus f at the original value, which was 1, 2. So let's all maybe take a minute to do that. And I'll do it too. I'm just going to try to do it without a calculator, but feel free to use one. 4-1. 4-1, thank you. 4-1. Minus, is that -3? Oh gosh, that's not meaningful. Why am I being such a whim about it? Is it -3.8? No, 6? Is that right? Somebody tell me if that's right or not. Oh shit! Look at this. Did I get that right? Check out my math. Yeah. Look at that. That's crazy. Why am I freaking out? What's that? Seems they're the same. Because it turns out that unless I miscomputed something, the exact change here, -0.6, is the same as the approximate change. Now, why this shocks me a little bit is because if you sketch this thing out, it's a saddle. It looks like a saddle like that. So it just seems really shocking that the tangent plane would do a good job, but I guess it did. How do you feel about all this? So this is for getting quick computations. So now imagine you're doing some code and you know that you're always going to be working around the point 2, 1 or 1, 2. You know that all your inputs are going to be around here and you're interested in studying the change. You would compute the differential and then just use this equation. This is so fast compared to this. This has, well, shit, actually, it's actually kind of the same number of operations, now that I think of it. This is multiply, addition, multiply, addition. What's actually, hey, CS people, why would this one be better? What in computer science would make that a better thing to have? Why could I make it faster? So I'm trying to save my ass here, but it's true.
So first order.
What's that? What?
No.
How do you multiply by 2 in a computer? Fast.
Just add it together.
That's true, you could add it together. You could also shift the bits. Does anybody know what I'm talking about, or am I just saying stuff that like very few?
Are you just trying to do multiplication through like
Yeah, because it's binary. So this is just like shift the bits to the right once, and this is shift the bits to the, shift the bits to the left once, shift the bits to the left twice. Super fast. I'm just gonna stop. Let's move on to the chain rule.
Yes.
I should actually give you guys a problem to practice this stuff. I have to create some webworks to practice, so I will. Let's get to the heart of what I really wanted to talk about today.
So if we like
Yes,
wanted
sir.
to actually program that, we just have like a step size for the DX, and it just like takes a bunch of like steps.
Yeah, that could work. Yeah, absolutely. Depending on what you want to do, but yeah, absolutely. It'd be cool if I could have some coding assignments, but maybe we need, I think I thought about this a long time ago, a Desmos assignment where you create an app. That does sound kind of cool. I think it's getting to the place where we know enough that we should be able to do something like that. And we can decide on it without Alexander here, and then he'll have to live by our decisions. What's that? What's going on over there?
Just
You know-
sneezed and then he blessed me.
He blessed you?
He blessed me.
Wow.
He sneezed.
Okay. I was like, did you gain some sort of mystical powers over the break? You had a good break, sir. That'll do it. Or it'll do the opposite. Chain rule. So, got a bunch of variables all linked up. in a chain of compositions. So let's say, for example, I know that z equals, oh hell, x squared minus y squared. That looks familiar, sure. But then x itself depends upon some other variables, u plus v. And y depends upon u and v, but in a totally different way. I might be interested, we know how to find the change in z if there's a little change in x and a little change in y. We just literally talked about that, differentials. But what happens if there's a little change in u and a little change in v? How do I propagate the changes from these inputs here to the final output? So let's look at the chain of dependence. And you're gonna wanna always write these pictures out. So first off, z is our final ultimate output. And z depends upon an x and it depends upon a y. Each of x and y, now you could put over here a u and a v and share them, but I think it kind of helps to make these look a little separate, even though they're actually the same. So I highly recommend when we're doing this stuff, create chains of dependence. Because this one, what if I had another layer? It just helps keep your brain straight. So what we want to do is find some things like this. What is the partial derivative of z with respect to u? What is the partial derivative of z with respect to v? Let me wait till everybody's getting that written down, because one thing I could do is, I'll show you what I could do. What I could do is rewrite the z formula. So we could rewrite z in terms of u and v. We could do that. Let's just go ahead and do that really quick here. So z would equal u plus v quantity squared minus u times v quantity squared. And all I'm doing is plugging in the x and the y formulas. And from here, I could actually crank those things out now. Does that make sense? Because now I've got z in terms of u and v, and I could just do the partials as I need. But we're going to do this in a slightly different way. So the partial of z with respect to u, look at the chain of what's on top and what's on bottom of the partial, and follow the path to get there. So in other words, to get from z to u, I've got to first take the partial of z with respect to x. So I'm taking the partial of z with respect to x. Now I've got to do it with respect to u, so I say times. And this is like the outer part. When you think of chain rule, you often think derivative of the outer times derivative of the inner. So we could even think that way here. This is the outer part times the derivative of the inner part, which is the partial of x with respect to u. And so this is my inner. And I want you to also notice it looks like the partial with respect to x cancels. So like the way I always did physics, because it never made, I did like, what is mass? Who knows? I don't even think physicists know. So there's all sorts of weird shit that doesn't like make sense. It's all strange. But as long as your units work out, you're probably right, right? Like that's like you just make sure your units like, oh, I need work. So I know what works units are. So I've got a bunch of shit, I put it together in the right order to get me the right units. Same thing here. You can think of these things as canceling. Hey, could you do me a favor and write out the partial z with respect to v formula? And use the chain. Oh, shit, actually got one more, sorry, let's hold on. Because there's actually one other u that it depends upon here. So I actually forgot, plus partial of z with respect to x, I got so excited about my little thing I was telling you there, times partial of, with respect to y, times partial of y with respect to u. And again, the partial with respect to y's look like they cancel, but you want to hit every single branch here. You want to make sure that you've got all the branches covered. So go ahead and try the partial with respect to v and realize that you need to hit the x and the y branch. I hope that's making sense. There's nothing deep going on there. I mean, there kind of is, but in terms of just getting rhythms of symbols, we got it. Let me give you a challenging one. Let's keep this up because I kind of want to come back to that. What if I also had u equals sine of st and v equals s minus t? So what's the ultimate output that I'm going to have? What's the ultimate output is z, the ultimate input, the base level input is what I'm meaning to say, is s and t. So how could we do partial of z with respect to t? So now you got to add another layer here. So each of these depends upon an s and a t. So you want to take all the branches that link from z to t. There's going to be a bunch here. This is going to be quite a bit. I think you should have 4 things in your sum. So you just want to travel along every path that links z to t. And if you keep that diagram there, you can't really get lost. And you add the results together, just like they're differentials. Does this feel okay? Let me stop. Let me let everybody take a minute. Because I do have a problem. Let's see, did I think I feel like I had a physics. Oh shit. A hot metal plate. Yeah. Good stuff. Also bought a new thermos. highly recommend Zojirishi. Everything. Sorry, Christian, am I in your way there? Go. It's all good? Okay. Metal plate.
That one, we got 7th place.
Oh yeah, Kirkman told us.
Did he?
What happened?
We're in the cybersecurity club. There was a competition in spring break.
Oh, cool. You guys got 7th place, or?
It's like the second round of the.
Yeah, this is technically the semifinals, right? Because then next is just nationals.
Yeah.
Oh, congrats. That's cool. Yeah,
We
yeah.
didn't last, so.
Yeah, we-
Yeah,
we
it's,
thought we were gonna get
that's
last.
something.
We
That's
thought we were
something.
gonna get last.
So you're done. You don't have to keep doing it
Yep.
then. That's also
Well, we have
what? That's
bi-weekly club meetings now,
Oh,
Oh, was it bi-weekly?
so. Yeah, I don't want to do weekly.
Yeah.
I'm sorry.
Sorry, Dr. Gray. I'm not doing weekly.
I'll send him a link to the class recording for today.
You'll understand.
He will. He doesn't even have time to watch it.
Probably not.
Probably not. So is there any questions on this answer right here? Does everybody see how we got the 4 pieces and how to keep track? Okay. So here is a real life problem in quotes. There was some ant walking on it, so it's actually just nonsense. Suppose the temperature on a metal plate is given by t of x comma y. So x, y are your x and y coordinates on the plate. We're assuming we've coordinatized the plate in some way. I think we'll probably just assume it's like this. So here's your plate. I kind of think it's actually an infinite plate too. Why not? Let's make it as unrealistic as actually possible. So it's an infinite metal plate represented by the first quadrant here. This is my x direction, this is my y direction, and so here's the plate right here. The temperature at point xy is given by 100, and this is going to be in Fahrenheit, of course. Because an old man made this up, old man who uses English units. What were the units you gave me the other day? There's some weird ass.
Furlongs.
Yeah.
Furlongs?
Furlongs. X and Y could be in furlongs here, but they're not. So this is in degrees Fahrenheit, and X and Y are in feet. If you're going to use Fahrenheit, you just go with feet. It feels like. Once you're going to go fogey on one of these, just stay fogey on all of them. So, an ant walks in a straight line, even more realistic, all of this, in a straight line from 1,4 to 5,6. Now I'm gonna have a bunch of stuff for you to do here, so it's gonna pull together a lot of things that we've done. That's what I like about this. Find the instantaneous rate of change, so derivative, in temperature with respect to t, little t, time in seconds. And do this when the ant is halfway along its destination from 1,4 to 5,6. So the ant is going like this. What's the first thing we need to do? Let's problem solve. What's that, Cormac, you want?
Find the halfway first.
Oh yeah, we could totally do that. How would you do that? It's not a bad plan. How do I find halfway point? Yeah.
Well, 1-4 is your starting point, 5-6 is your end point, you get like half, 5-6.
Have this,
Yeah,
so 2.53. Is that what you're saying?
that should be happening.
Let's see, so 2.53, oh, I don't think that's on there.
Oh,
Should be.
I like the thinking we're doing here, though. What should it be? What do you think, Kayla? You're saying stuff, but it's silent.
Well, we can find the like length in between the 2 points of Pythagorean theorem, and then find the points that
Oh boy, we could do that. That sounds super painful. But we could totally do that. We can take the length of this right halfway and then figure it out. Oh my goodness. There's gotta be something simpler. Cormac, what are you thinking now?
Would you have the change in x and have the change in y?
We could do that too. Or we could just take the average of the coordinates, and that'll get us halfway and halfway. So if you take 4 plus 1, so this is how we would do it, Daniel. We need to incorporate this original start piece, so you have the right idea. But halfway point would be 3, 5. And you notice that 3, 5 probably is right on there. So that's good, but how are we gonna find rate of change with respect to time if we don't even have time yet? So there's temperature, depends upon position. How do I introduce the variable t into this problem? Let me erase one thing. What is moving? What's moving? The ant. The ant is moving. How could I predict the ant's position at any time t? Give me a formula. Take a minute and think about this. What we need is a formula for the ant's position, x of t, y of t equals. Give me a formula. Take a minute. And let's say that at time 0, the ant's at 1, 4. So x at 0, y at 0 equals 1, 4. And I don't care, he could get there to the other point at any time. We won't try to get fancy and make it like 1 second or something. Take a minute and think about this. So parametric equations, right? We've kind of done some of this before. We might have even found the equation of a line between 2 points in parametric form. Just saying. Just saying I'm gonna go run to the restroom. I'll be right back. Had a lot of tea. Think original location and vector of change. I won't say any more. No, I'm just kidding. got some? Take a note. Anybody got a position? Where's the end at time 1? Where's the, I need a formula for the end. Maybe I better draw some pictures to help. The ant's moving that way, we could assume that, right? It's not necessarily true, we don't quite know what direction the ant's headed, but it's okay. It will affect our answer, I guess. Oh, no, we do know what direction the ant's headed. Yeah, I said from 2, so we're good to go. Not just traveling. How do I get the equation of a line in space? R of t equals?
Rise over one.
X.
That's like, yeah, that's definitely rise over run. I could use point slope form. That's a little old school, but it's true. How do I do it in vector form?
Point plus time times direction vector.
Exactly. So point on the line plus direction vector. And then here I could put t minus t naught or t, either, all of those work. So t, that would work. What's my direction vector?
5, 6 minus 1, 4.
It's 5, 6 minus 1, 4. Exactly. So let's start getting here. What point should I use as my original point? Where's the origin? 1, 4, yeah. So we could do here, we could even write this as vectors. 1, 4 plus. So our direction vector is going to be 4, 2. Does that sound right, T? At what time am I at the second point? How long does it take the ant, according to this parameterization, to walk from here to here?
1 second.
1 second. How could I change that if the ant was walking slower? What would I change about this? If somebody told me, oh, it takes like 10 seconds for that to happen, how would you modify that equation?
Divide the direction vector by 10.
Yeah, divide by 10, you can scale it by 10, right? So if I wanted the ant to arrive at the second point by 10, I could literally just divide that by 10. Still gets me to the same place, just moving slower. And as someone said, do this into the direction vector, right? So just put that in the direction vector. Think of this as your velocity vector, right? This is your velocity. Okay, so now at least we've got something here. So let's write up here in vector form, xt is equal to 1 plus 4t, comma 4 plus 2t. Things are starting to look up. They're shaping up in our world. The ant's walking at a constant velocity. What time does the ant hit the halfway point? 0.5 seconds, right? Takes 1 second to walk from here to here if you're doing a constant velocity. The midpoint would be at t equals 0.5. So now we've even got that. So what we need next is the instantaneous rate of change in t. So here is where I need the chain rule. So the chain rule says that the partial of t, now there's going to be a slight twist here, so actually let's draw out the correspondence, right? So I've got t depends on x, depends on y, and each of these depends on only one other variable, and that's t. They both share the same variable t. So when I write out the chain rule, this derivative here is going to be partial, but the derivatives of these with respect to t is a regular derivative. So let's write that out and then let's make a little note about it. So here, the partial of t, big T, with respect to little t, hit all the branches, equals partial of big T with respect to x, but since x only depends on one variable, it's just a normal derivative. You could put partial of x with respect to t here, but let's try to be more mindful about it. So here, that x depends on one variable, so regular derivative. And then that's plus, now I go down the other branch, partial of t with respect to y, and I'm using partial on t because it depends on two variables, times dy dt. Again, y only depends on one variable. So with all this, put some stuff together, make it happen. How freaking fast is the temperature changing for this poor freaking ant? That plate is pretty hot. And it actually becomes ridiculously cold. I think we hit like negative 273 Fahrenheit pretty fast, like absolute zero, pretty fast. Oh wait, is that negative 273, is that, that's
Negative 273 would be 0.
that's
for
0 Kelvin,
Yes.
0 Celsius.
0 Kelvin is absolute
Wait a minute, let me write this down.
0. 273.
0 K equals, so 0 Kelvin,
It's 0, absolute 0.
Well, it's just Kelvin.
and that's negative 273 Celsius?
Yes.
Okay, got it. Okay, thanks, thanks. Is there some kind of 273 stuff in there? It doesn't matter here. We're doing Fahrenheit, all goofy. But the temperature does become pretty terrible, and I'll show you why I know that in just a minute.
I don't know what negative 273 Fahrenheit is.
Yeah, you know, it doesn't matter either, does it? You know?
Just negative 2 Celsius.
What is it?
It's just negative 273 Fahrenheit. That's all it is.
That's all it is.
That's all it is.
It's enough. It's pretty bad. So you've got a few things you need to figure out here, and that's why I'm going to give you some time. I'm going to start handing some stuff back while you think this through. And these things I'm giving back to you, if you have corrections, I need those by next Monday. Let's try to keep up on these. I would like you to do retakes by the end of next week, please. Oh wait, some of this is new stuff. Some of this is stuff that happened. Sorry, Carmen. There's a lot of writing on here, and it all was just nonsense. You just ignore it all. I made this problem. I was like, that's wrong. But I made the problem so there is no curvature. I wanted you to have something more interesting than that. So that's all right. You rocked it. This is zero. Is it something or is it zero? The six, right? Okay. Why don't I separate those so many needs to get back? That's- And always make sure that these grades have been recorded when you get them. You think you got that temperature change already? Feeling good on it? Oh, okay. Oh, it's okay. You seem like a man who had nothing to do. I just didn't want to.
Yeah, that's me every day. It's pretty normal, man.
Oh, Atman, where are you? What's that?
He said it gets cold.
Really?
Do you remember the?
Okay.
It seems, feels like.
Cause
It does, a little bit.
You get like the negative.
Oh, there's a,
Yeah,
there's
there's
a-
Let's do this one, and then let's do, wait, let's see, Evan, this for Evan. Let's get through this together, and then let me give you another one. Oh, Lord. The first thing I do is just crank this formula out, right? You've got this rough formula, still have to do the work. What's partial of t with respect to x?
Negative 2x.
Negative 2x, so don't forget about that negative that's affecting both of those. So that's negative 2x. What is dx dt? Just 4. Does everybody see that? Here's the x. Partial with respect to t is 4. And then we're going to have plus, what's partial with respect to y of t? Negative 8y, very nice. Does everybody see that? Negative 8y? Okay, cool. And then partial with y with respect to, or derivative of y with respect to t is 2. What a beautiful formula, right? And the only thing I have to know is, what is the x and y coordinate at the time of interest? So you could, at this point, let's talk about things we could do. So first off, I should simplify to make that pretty. In this format, I need to know the x and y coordinates. But I actually have these formulas for them already. So if I wanted, I could turn this into a pure t formula. So make a note here. Note, x and y depend on t. But I can just go ahead and plug in what I know. X is equal to 1 plus 4t, and y is equal to 4 plus 2t. And now I've got this really beautiful formula in just pure t, and I can work with any time at this point. So let's see, so that's gonna be negative 64 minus 8, negative 72, 32, so minus 64t. So now I have a really nice formula for the change in t with respect to time. Whoa, there should be a t here. Where did my t go? Right there. So the temperature is always going to be negative. It's going to become more and more negative. Poor little ant is going to be pretty fried. We'll have to figure out what the temperature is at the point of the halfway mark. But we already talked about, if this is t equals 0, this is t equals 1, I just need t equals 0.5. So at t equals 0.5, we have partial of t with respect to little t equals just negative 72 minus 32. Ridiculous. And I'm just, the 32 comes from putting half in for the t. And so what is that? Negative 104 degrees Fahrenheit per second. That's pretty brutal. But that's what the answer is.
Take it through into space. Just like
Yeah, it's
cold.
really bad. It's really bad. Because, so like, let's understand this a little bit more. It's a really goofy problem. And I'll be honest, I grabbed this problem from somewhere. Honestly, I'm not trying to hide where, I just don't even remember where. Might have been a calc book, something. But if I look at the level curves here, they're gonna look like, let's see, let's take a look at the level curves. They are going to be in this shape, they're ovals like this. And let's see, when x and y are 0, the temp in the center is 100, so that's 100 degrees Fahrenheit right there. As you move away, that temperature drops. So as x gets bigger and y gets bigger, you're subtracting more and more off of 100. So the temperature is like precipitously dropping. Let's see exactly where's the temperature 0. So T equals 0 where 100 equals this. And you may or may not be aware of how to make that look prettier. So I divide it through by 100. I'm looking for the general shape of an ellipse. I'll show you where I'm going. So if I have something that looks like this, this is an ellipse with an x-axis, an x radius of a units. So if I go a minus a, and a y-axis with b as the radius. I'm using radius in quotes here. So you get an ellipse that looks like this. So our ellipse has a radius of 10. Notice how that's squared underneath, a squared and b squared. So this would be 10, this would be 5, and that's not very far, but all along here, the temp equals 0. So all along this ellipse, the temperature is 0. As soon as you move past that, the temperature starts to plummet and never stops plummeting. So out here, T is less than 0. Here, T is greater than 0. And where's our little Anty? Where is he? I guess he's still inside here. So little Ant's doing something like this, but it's getting pretty bad for him. And the temperature's really steeply decreasing. Like literally, if you move 10 feet in this direction, you've gone down 100 degrees Fahrenheit. 5 feet this way, down 100 degrees Fahrenheit. So that's why the rate of change is insanely fast, insanely large magnitude. All right, that's enough. So you have two partial derivatives using the chain rule defined for Wednesday before class. So new thing, again, the quizzes before class are going to be bringing you back to what we covered the last time. Instead of you going in there and like just putting down anything just to get something down, because I know that's what's happening, because how could it not be? How could it not be? All right, let me just get these, oh, sorry, Robin. Let me just get these all back to you. So if you just wouldn't mind waiting a minute. I would hand these around, but I don't want to like do FERPA violations as part of the regular class. Do FERPA violations.
Thank you.
Just today with consent.
Could yeah.
You can ask him when can I just hand it out? And if there's anything he doesn't mind, we'll privately.
I feel like it might almost take longer too, right? Like if I give you these, find all your stuff. I'm not sure, it's a good, I like your thinking. I like the way you think.